Mm. All right, everybody, we're back at it this week with continuing on with moles and stoichiometry. Are we gonna get started, please? Everybody hear me? All right, I know it's last week before spring break, but we got to focus a little bit. All right, so before I start with the material today, I wanted to just let you know about some things upcoming, which is the net result being I won't see you guys for a while. So this week, Wednesday, I have some research related travel that will take me out. So I'll have a substitute in here on Wednesday, Professor Yang, I'm sure I pronounced his name. But then I also have notes and a recorded lecture posted so that if you want to maintain the continuity of how I teach everything, you'll be able to do that on your own. And then same thing the week after spring break, something else research related, something totally different. They just all kind of clustered up on me. So after spring break, it'll be the same story. We'll have substitute lectures for both days and recorded stuff available online if you want to follow on that way. But you're still encouraged to come to class where they will cover the same material, just in a slightly different format. So I apologize for that. I don't like to miss class during the semester, but these things were important and just poorly timed that I couldn't really avoid it. But after that, I'll be here the rest of the way, so you won't miss me too bad, I think. All right. So then we're going to go on today with stuff that is following up on what we talked about last time. So the topic we ended with last time, we were talking about moles, and especially moles to mass relationships in chemical formulas. We learned how to take the chemical formula of a compound and determine the mass percent of every element in that formula. Now, today we're going to learn how to do the opposite process, which is to take mass percents that are given to us and convert them into a chemical formula. Now, the first thing we have to recognize, though, is that when we do this, we're a little bit limited in terms of what information we can get. We can't actually get from that information alone the full molecular formula. We can only get what's called the empirical formula. So just as a reminder of what we're talking about and as a definition of what empirical formula is, the molecular formula tells us the total number of each atom in a molecule of a compound. And that's pretty self-explanatory, but that tells you if you have one molecule of that compound, here's how many of each atom are in there. We can also interpret that in terms of moles, as we said. Now, the empirical formula is the lowest whole number ratio of atoms in a compound, which on its own is not that useful of information, I suppose, or it's not nearly as useful as the molecular formula. But as we'll talk about today, if we're using mass percents to figure out the formula, this is the best we can do. So for covalent molecular compounds, we don't typically report the formula this way. As I said, it's more limited in terms of the information it gives us. For ionic compounds, though, this is exactly how we would report it. So we talked about with ionic compounds, you want the formula to be the lowest whole number ratio of all the elements. And so typically in an ionic compound, the empirical formula is the formula that's reported. So there's really no difference there, even though the terminology is different. But for covalent molecular compounds, compounds that involve nonmetals, in many cases, again, the empirical formula doesn't tell you the whole story. So as some examples here, if we have a molecular formula N2H4, which is a compound called hydrazine, but this would be the molecular formula telling us that one molecule of this compound has 2 nitrogen atoms and 4 hydrogen atoms. The empirical formula for this compound, though, that's not the smallest ratio, 2 to 4. We divide by the greatest common factor, which is 2. And so the empirical formula of this compound will be NH2. Now, again, NH2 does not actually tell us what the structure of that molecule is, but it tells us the ratio of the 2 elements, 1 to 2. And as we'll get to, if we're using mass percents, this is the information we can get. For some covalent compounds, the molecular formula and the empirical formula are the same. So for a simple molecule like water, which is H2O, we always want to maintain whole number subscripts. We never want to go to fractions. And so in this case, there's nothing you can do to those. 2-to-1 is the smallest ratio you can get to. So for water, H2O, the empirical formula and the molecular formula are the same. So that's certainly not impossible. And then for other things, we talked about benzene in class at the end of chapter 4, the sort of hexagonal 6-membered ring compound that has pi delocalization. This one has subscripts of 6 on both, so the greatest common factor is 6, and there's an empirical formula of CH. And then for B3N3H6, and a compound that's actually somewhat related to that, although not obvious that's the case. Again, this time there's a common factor of 3, 3, and 6, so we can reduce the empirical formula to BNH2. Now, as I said, usually we don't go in this order. We don't usually take a molecular formula and determine the empirical formula. That's not a very useful thing to do. But what we are going to be doing is finding a way to determine the empirical formula. And then with additional information, we can figure out what the molecular formula is from there. But the important part is to recognize that the molecular formula is always going to be some whole number multiple of the empirical formula. So if you have an empirical formula of CH, the molecular formula could be CH, C2H2, C3H3, C4H4, and so on. Some multiple of CH would be your empirical formula. And with certain information we can give you, you'll be able to figure out what that is. So that's the relationship between molecular formula and empirical formula. The important thing for today is to learn how to determine the empirical formula using mass percents. So the typical way we do this is we will give you information about the masses of each element that are in a compound, either in raw numbers, there's this many grams of this element, this many grams of that element, and this many grams of the other one, or in terms of percentages, we might say that this compound is X% carbon, Y% hydrogen. What's the empirical formula? So we're going to give you some information about the masses or mass percents of the elements in that compound. And that's information that we had introduced starting as early as chapter 1. We covered mass percent way back then, and we learned what it means, and we learned about the mass laws that are related to that. Now we're going to talk about how do we take that information and convert it into the actual chemical formula, which is much more valuable for us to have. So the first thing you're going to do is convert the mass of each element to moles. So again, you're going to have some information about masses, either in absolute terms or as percentages. So you're going to convert the mass of each into moles. And as we talked about last time, that requires us to use the atomic mass of each element, which is the number of grams in 1 mole. We use that as a conversion factor. The second step is we're going to get a bunch of mole amounts that are likely not going to be in whole number ratios. We have to convert those to the lowest ratio possible by dividing by the smallest one. So you're going to have mole amounts for each element, and you want to get it to the smallest ratio. I should say smallest, not lowest ratio. That's a better way to say it. You're going to take each molar quantity that you get from step 1 and divide it by the smallest one of those. We'll illustrate all these steps a few times today, so if they don't make total sense as I describe them, you'll see them illustrated in a bit. Now, the third step is if necessary. So sometimes you do step 1 and step 2, and you get an empirical formula that has all whole numbers in it, and you're good to go. Now, other times, though, after step 2, you're still going to have some fractions or decimals, and you need to do this third step, which is, again, listed here as if necessary, not always required. You're going to multiply those results, all of them. We're trying to keep the ratios all the same, so we can't, if we multiply one number by something, we have to multiply all of them by the same thing. We multiply by a small number, which you have to determine what that is, just sort of by inspection, to remove any fractions or decimals that you have. Now, this is important because one of the common mistakes that people make when they're doing problems like this is they do too much rounding. If your number is not really close to a whole number, like within 0.05, 0.1 of a whole number, you don't want to necessarily just round it up. So as an example, if you get, after this step here, if you get C1.5 H2 as the result from step 2, okay? Now, a lot of people make the mistake of, oh, well, 1.5 rounds to 2, so my empirical formula is C2H2. But that's too much rounding for a problem like this. If you want to get to whole numbers in this situation, we need to find some factor that we can multiply these by to get to whole numbers. So if you have something 0.5, then the obvious thing to do is to multiply that whole thing by 2. So you have to multiply the entire thing by 2, not just one of them, both of them. And that gives you then a whole number empirical formula of C3H4. Okay? Get rid of the fraction or the decimal in that way, not by rounding. Again, if it's really close to a whole number, like, and we're not going to give you numbers that are that ambiguous either. Like if you do all your math and you get a number that's like C 1.99, well, okay, round that to 2, that's fine. We're not going to give you anything that's that. Everything we're going to do is pretty clear cut here. But if it's far away from a whole number like this, or another example would be, let's say you have n 0.66667 h. All right, and again, temptation might be like, oh, well, that just rounds up to 1. We'll just call it nh. But again, that's too much rounding. If you see something 0.33333 or something 0.766667, the obvious answer is to multiply everything by 3. So that would give you N2H3. I don't know if there's any compounds that have that empirical formula, but that's how you would approach it in this situation. All right, so I just picked some random examples to show you that. So usually, where you'll see this is you'll have a decimal that's something like 0.5, 0.25, or 0.75, or 0.33, 0.67 that you can multiply by a small whole number to get rid of the decimal. So you'll see some things like that. I don't think we see that in the examples we do today, but just so you're aware that it could come up, and not to do too much rounding, which is a common mistake that people make in this part of the course. All right. So let's just go through an example of it. So as I said, one way that we can present the information to you is via the raw masses of the elements in a compound. So this is a compound called vanadidyl chloride, and we find that a sample of this compound has 1.47 grams of vanadium, 0.462 grams of oxygen, and 3.07 grams of chlorine. What is the empirical formula? All right, so this time we're just giving you the actual masses that are involved, but the steps, whether we have masses or mass percents, are the same. And the first thing to do is for each element in the compound, find out how many moles do these masses correspond to, which is something we learned how to do last time. So we're going to find the moles of vanadium, oxygen, and chlorine. And so to do that, we start with the mass that we have, which is 1.47 grams for vanadium. And we're going to use the atomic mass to convert to moles. So we want grams of vanadium to cancel for 1 mole. And so we need to put the atomic mass in the denominator for that to work. So we have to look that up on the periodic table. That one I don't have memorized off the top of my head. V is right here, 50.94. So that's going to be the atomic mass that we would use for vanadium. All right. So we divide by atomic mass, a conversion we learned last time, and we get 0.0288 moles of vanadium. Okay. We do the same thing for oxygen and chlorine. So I won't flip back to the periodic table a million times, but for oxygen, we have the mass that we're given is 0.462. That's directly from the problem. 1 mole of oxygen has a mass of 16.00 grams. That's the atomic mass that we would look up on the periodic table. And so we get an almost identical amount of oxygen, 0.0289 in terms of moles. And then the last one in the formula is chlorine, atomic symbol Cl. So we have 3.07 grams of chlorine in this compound. We're going to use the same step. We're going to divide by the atomic mass to convert grams to moles. Chlorine on the periodic table is 35.45. So that gives us a different number this time, 0.0866. All right, so those are the moles of each element we have. Now, an empirical formula, as we said, should have whole number subscripts. These are anything but. So the next step, which we listed as step 2 in the step-by-step approach that I outlined, is to divide each of those by the smallest. So it wouldn't be technically wrong, but it would be highly unconventional to write the formula in this way. V 0.0288, O 0.0289, Cl 0.0866. that is technically the empirical formula of that compound, but it's in a completely non-standard way with all these decimal subscripts. So we're going to divide each of those by the smallest one. The smallest one is 0.0288. So we divide all of them by that same number. Once we get to this point, any operations we do on one has to be done to all three of them. So that's sorry, it's 88. Not that that changes. And then, so we divide all of those three by the same thing. And what we end up with, in this case, you're going to get like 1.0001 or something. So again, that can round to 1. And you end up with V1, O1, and then Cl3. Again, there might be a tiny amount of rounding necessary, but that should come up pretty close to exactly VOCl3. So we don't need that last step to convert that at all. It's already in whole numbers, already empirical formula at this point. So that's the steps we would follow. Convert each to moles and then find the smallest ratio of those and express it as a whole number. So any questions on that one? All right, so the next one is almost identical, just with mass percents instead. So here we want to know, what is the empirical formula for a binary compound consisting of boron and fluorine that is 15.94% boron by mass? Now, this one you might be a little bit confused because like, well, there's two elements in the compound, boron and fluorine, but only have 1 mass percent. So there's a couple key words here. First of all is that because it's described as a binary compound, that means there's exactly 2 elements in the formula. And then what we have to also remember is that when you have mass percents of elements in a compound, they all add up to be 100. So if we gave you the mass percent for boron is 15.94, by difference, we can figure out what the mass percent of the other element is just by subtraction. So the mass percent for fluorine, they all add up to 100%. 15.94% of that is boron. So that's going to leave us with 84.06% fluorine by mass. All right, so we don't give you all the mass percents. That's why they all add up to 100. In this case, there's only 2 of them, so we find the other one. So in a problem where we give you mass percents of the elements, it's almost exactly the same set of approaches. It really is in essence. But these are percentages, not grams, but we're going to just assume that we have 100 grams of the compound. These mass percents, as we said last time, are intrinsic properties, so it doesn't matter how much compound you have. So if we assume 100 grams of the compound, then the percentages tell us exactly how many grams of each element are in 100 grams of compound. So for problems like this, we just use the percentages as gram amounts because we just assume that we have 100 grams of the whole compound, and each percentage that we have would be the mass amount of each element. So we're going to do the same steps again that we did last time. So the moles of boron, we have 15.94 grams if we're assuming 100 grams of the compound. 1 mole of boron, we have to go to the periodic table again. So again, we look those up on the periodic table. Boron is 10.81 grams per mole. Fluorine is 19.00, thereabouts. So there's fluorine. So we have those 2 atomic masses that we'll need. So for boron, it's 10.81. So we can divide by that so that the grams cancel. And that gives us 1.474 moles of boron. We do the same thing for fluorine. We found its mass percent by difference, 84.06. So in 100 grams of compound, there's 84.06 grams of fluorine with an atomic mass of 19. .424. All right, those are clearly not whole numbers, and they're way too far away for us to round at this point. So we're going to, again, take the step of dividing all of them. So we have B 1.474, F 4.424. We divide those by the smaller one, which is 1.474. And that gets us to BF3. So there's 3 times as many moles of fluorine as boron. The smallest ratio would be BF3. All right. So that's the steps we take for mass percent, which again are identical. We just convert the percentages to grams by assuming that we have 100 grams of compound. All right. So that's how we get the empirical formula. Now, if we want to get the molecular formula of something, there's going to be one additional step that's needed. So typically for molecular formula, you're going to find the empirical formula, From that, you can get the empirical mass by just adding up the atomic masses of the elements. But then to convert it to the molecular formula, you also need the molecular mass. So in a problem like this, if we want you to find the molecular formula, we also have to give you, typically, there's really no other way to do this, the molecular mass or the molar mass of the compound. And then from that, we can figure out what the formula is. So as an example of that, let's say we work through a problem similar to the one above, and we found that the empirical formula is CH2. We want to know what's the molecular formula. Well, if we want to know the molecular formula, the other information you need is the molecular mass, which we're given here is 70 AMU. So in a situation like this, where you've gotten we've gotten the empirical formula, and now you want to find out what the molecular formula is, what you're going to do first is find the empirical mass from the empirical formula, which again, on its own is not a very meaningful quantity, but in this type of problem, you'll need it. So we're going to calculate the empirical mass, as I'll call it, the mass that corresponds to the empirical formula, where we're going to take the atomic masses of the elements in the empirical formula and add them up. So this empirical formula has 1 carbon, and the atomic mass of carbon from the periodic table is 12.01 AMU. There are 2 hydrogens in the empirical formula, and its atomic mass is 1.008. Again, those numbers come straight from the periodic table. So we don't need to be real precise here because the given molecular mass has no decimal places. So that comes out to around 14 AMU. 12 plus 2 times 1. 14 AMU is close enough. So then to figure out what the molecular formula is, we're going to take the molecular mass that we're given, divide it by the empirical mass that we just found, to figure out what is the small whole number that relates the empirical formula to the molecular formula. So 70 AMU is the given molecular mass. 14 AMU is the empirical mass that we just found. So 70 divided by 14 is 5. So that tells us that our molecular formula in this case is the empirical formula CH2 multiplied by 5, which would be C5H10. Again, the molecular formula could be any multiple of CH2, but if we know the ratios of the molecular mass and the empirical mass, that tells us what multiple we should use. So that's the one additional step that you would need if the problem asks you to also find the molecular formula. Mass percents or masses of elements can get you to the empirical formula. This step is required to get all the way to the molecular formula. So then to put it all together, let's finish this off with a problem that incorporates both of those. So we have a compound here that's 28.18% manganese, Mn, 30.80% carbon, and 41.03% oxygen. You can double check that those add up to 100, which they do. We're very close to that. And then it has a molar mass of 389.98 grams per mole. Determine the molecular formula. So there is these steps are a little bit, these problems have a little bit of steps involved. So we have to go through the first series of steps to find the empirical formula. So we're going to assume 100 grams of the compound. Then we're going to convert each of the mass percentages into moles. So for manganese, we have 28.18%. So there's 28.18 grams of manganese in 100 grams of the compound. And we're going to use the atomic mass to convert it into moles. So manganese Mn, the middle of the transition metals, is 54.94 grams per mole. So we need that number to convert grams into moles. So we get 0.5129 moles of manganese. For carbon, we have 30.80 grams in 100 grams. Carbon has an atomic mass of 12.01. We've seen that one already. So the molar amount for carbon is 2.564. And then the last one is oxygen, 41.03 grams. Atomic mass of oxygen is 16 grams per mole, so we divide by that. That comes out to the same number we got above, 2.564. All right, so those are the moles of each element. And then we can convert that to an empirical formula by dividing all of them by the smallest one. So manganese, 0. I'll just round a little bit. You don't need that many decimals at this point. Carbon, 2.56. Oxygen, 2.56. We're going to divide all of those by the smallest one, which is manganese, 0.513. And we end up with manganese C5O5. So that's the empirical formula, which is the smallest ratio of the elements, but we also want to know what is the molecular formula. That's what this problem is asking for. So the next step, as we talked about in the previous slide, is to use that information to get an empirical mass. So we're going to take this empirical formula here and determine the molar mass that's associated with that. So we have one manganese, which has an atomic mass of 54.94. We have 5 carbons that have an atomic mass of 12.01. 5 oxygens that have a mass of 16. So the empirical mass is 195.00 grams per mole. And then we divide the given molar mass by that to figure out what factor does our empirical formula need to be multiplied by. So the molar mass over the empirical mass. The molar mass was given as 389.98. The empirical mass we just found was 195. So to a good approximation, that's a factor of 2 difference. So that means that our molecular formula is 2 times the empirical formula. So we come back up here. This was our empirical formula. We double the whole thing. We double all of the subscripts to get Mn2C10O10. So that will be the correct molecular formula for this compound. All right, so there's a lot of steps involved. In addition to converting to moles and finding the smallest ratio, you have to go through and do the empirical mass and compare that to the molar mass. So a lot that goes on there, but that's the series of steps we would follow. None of them on their own are too difficult. Just piecing them together can be a little bit challenging. Now, this is the first time in this course we've had a lot of multi-step problems like this. So sometimes there's a question of like, well, how much should I round and all this stuff? My recommendation is as you're doing some intermediate calculations, keep at least 3 significant digits as you go forward. You don't have to go crazy and keep like 12 decimal places or something like that. We're not going to grade you that level of precision ever. Typically numerical problems is if you're within 1 or 2% of the answer, that's fine. This one, you're just getting a formula anyway. But just to make sure you're not doing too much rounding and losing too much precision in your final answer, I would say for intermediate steps, try to keep at least 3 or 4 significant digits. We don't grade you on significant figures anymore after chapter 1, but to make sure that your answer is close enough to the right answer, you want to make sure you're not aggressively rounding everything too soon. So keep 3 or 4 digits at least to make sure that your answers are okay at the end. All right. Any questions on that or anything else related to that? All right. So the next major topic is related to this, but it's a more indirect way of getting the same information. So and the reason we introduced this is because this is really a real experimental technique that people use. So especially for organic compounds that have a lot of carbon, hydrogen, and oxygen, that's when it's most common to do this. One way that we can determine experimentally what are all the mass percents of the element, and then how does that eventually get us to a chemical formula, is to do what's called combustion analysis. So basically you take an organic compound of some sort that you're trying to identify. Again, usually it has a lot of carbon, hydrogen, sometimes some other things in it, and you set it on fire. And that's what you're doing. And then you carefully collect all of the gases that come out of that combustion reaction. So ideally, all of the carbon that's in the compound will be released as CO2 as the final product. So when you burn something that has carbon in it, it makes CO2. Any hydrogen that's in the compound is going to come off as water vapor. And you can then measure how much of each of those there are. And then by difference, you can figure. So basically, all the carbon comes from the CO2. So you figure out how much carbon is in the compound by measuring how much CO2 is produced and then backing out the mass of carbon that corresponds to. We'll show you how to do this. You measure the amount of water vapor that comes out during the combustion, and from that, you can get the mass of hydrogen in the compound. And then finally, for any other stuff that's in the compound, whether it's oxygen or other elements, you can really only do it for one other element precisely. You have to do that by difference. So you know the total mass of compound that you started with, and you subtract the mass of carbon, and you subtract the mass of hydrogen for that to get the mass of everything else that's in there. So again, it only works if there's only one other element where you can precisely find that with just this technique alone. You do have to do that for oxygen because oxygen, when you burn something, you're using oxygen from the air as a reactant, and it comes out as both CO2 and water. So you can't back out the amount of oxygen directly from the combustion analysis. But by difference, you can get it, or if there's other elements besides carbon, hydrogen, oxygen, you can get them that way as well. So this is a technique that allows us to determine the empirical formula of an unknown compound, or to at least confirm that the composition that we have lines up with what we're expecting. So we do still use this in research today. This is not, some archaic, ancient thing that we're teaching you for no reason. It is a technique that is still employed. It's not the most satisfying experimental technique because you might take weeks or months of your hard labor making a precious compound and then you set it on fire to analyze it. So you're burning your precious material up into the air, but from that information you get some useful data that can either determine or confirm the composition. So again, these are also kind of steppy and tedious. They have a lot of steps involved, but it really still is just mass to mole conversions that we're doing, just in a slightly less direct way, because here we don't directly give you the masses of the elements. We give you the masses of combustion products, and then from that you back out the masses of the elements that are involved. So let's see how to do that. Again, usually examples are the best way to illustrate a lot of this stuff. So we do combustion analysis on a compound that has carbon, hydrogen, and bromine in the formula. And we find that a 5-gram sample of the compound, when we burn it, produces 0.871 grams of carbon dioxide and 0.179 grams of water. What is the empirical formula? So that's the typical setup of a combustion analysis problem. You know how much mass of the compound you're burning, and you know how much mass of CO2 and water are produced. And that's the sort of the numerical inputs and outputs that you would get. All right, so again, in this case, we have carbon, hydrogen, and then bromine would be what we classified before as the other stuff that I have to do by difference. So the first step is we're going to find the mass of carbon. Now, I would say that in a problem like this, if you have only carbon and hydrogen, you don't necessarily need to find the mass of carbon. You can just find the moles and be done. But because we need to find the mass of bromine by difference, we're going to need the mass of both elements also. So this is really the full set of steps you would have to do, even though in some cases you can skip or shorten this first step a little bit. All right, so for the mass of carbon, we're going to start with the mass of CO2 that's produced, because all the carbon that was in our formula is going to get released as a product in the form of CO2. So when in doubt, the first thing we do is convert to moles. So we're going to convert the grams of CO2 to moles of CO2. And for that, we use the molar mass of CO2, or the molecular weight as it's sometimes called. So for CO2, we have 1 carbon in the formula, 2 oxygens. So when we add those up, we get 44.02 grams per mole. Okay, so we're going to use 44.02 grams per mole as the molar mass of CO2. That gets us moles of CO2, and then from there we can use other information to get the mass of carbon that's in there. So we want to find moles of carbon next. This is a trivial conversion, but because the formula of CO2 is CO2, there's no subscript in carbon, which tells us that 1 mole of this compound has 1 mole of carbon. So this is kind of trivial, but that would be the next step. Convert moles of CO2 to moles of carbon. So you have that many moles of carbon, and then from there, the atomic mass of carbon gets us back to grams. So we have 0.238 grams of carbon. So 0.871 grams of CO2, 0.238 grams of that is carbon. We're going to do the same thing to find the mass of hydrogen. The combustion reaction produced 0.179 grams of H2O, water. We use the molar mass of water to find the number of moles of water that corresponds to. 2 times 1 for hydrogen plus 16. So the molar mass of water is basically 18 or 18.02 if we want to be more precise. So again, make sure you know how to find molar masses. They might be given to you in some problems, but other cases they won't be, so you have to be able to find them just by adding the atomic masses. That's moles of water. But we're trying to find how much hydrogen there is. So now we're going to convert to moles of hydrogen. Here's where you have to be a little bit careful because this is the one slight difference here. The formula of water is H2O. So the 2 on hydrogen tells us that 1 mole of water has 2 moles of hydrogen in it. So we have to make sure we do this step here to get the correct number of moles of hydrogen. And then from the atomic mass of hydrogen, we can get back to grams, which is, again, basically 1, so a trivial last step. Zero 0.0200. All right, so that's grams of carbon, that's grams of hydrogen. And then finally, we can get the mass of the other stuff, which is bromine in this case, by difference. We started with 5.00 grams of the compound. We found from our first calculation that there's 0.238 grams of carbon. And we found from our second calculation that there's 0.0200 grams of hydrogen. So by difference, we can get the leftover mass as bromine, 4.74 grams. All right, so now we have the masses of each element. And at this point, it just becomes a standard empirical formula problem. Once you have the masses of each element, you can go through the same steps we've already done and get empirical formula. So just to quickly review that, again, a lot of steps for these types of problems. So I don't envy you those that have to do these on the homework assignments, but they're a bunch of mole conversions. And then once we have masses of each element, we go through. So moles for carbon, we found there's 0.238 grams. We're really just undoing the last step of our calculation, where we converted moles to grams. Now we're convert grams back to moles by using the atomic mass of carbon. That's 0.0198. For hydrogen, we found that there was 0.0200. And the atomic mass for hydrogen is 1.008. So we're just converting grams back into moles. And again, to reiterate something I said before, but now that it's a little bit more clear, if the compound only had carbon and hydrogen in it, if it was a hydrocarbon, as we call it, which only has carbon and hydrogen, we could have just stopped these calculations up here. I can't cover up on the screen, sorry, as just moles and moles, and not have to do this last step to get grams. But we needed grams here to get this number. But now we're going to just undo that last calculation to get back to moles, and then we do the same thing for bromine. We found by difference that there's 4.74 grams of bromine in this compound. The atomic mass of bromine from the periodic table, and remember, that's where we look these things up. Bromine is over here, 79.90. So that's the atomic mass of bromine that we'll use to find moles. (0.0593). All right, we have moles of each element, and now we just have to find the smallest ratio to get the empirical formula. C 0.0198, H 0.0198, BR 0.0593. We divide all of those by the smallest of those, which is 0.198. And we end up with CHBr3. So it's really just a more roundabout way of getting the empirical formula, one that is experimentally relevant. This is how it's often done in real life, but you have to start with combustion data to find the masses of each element, and then from there you still have to go forward with all the calculations needed to find empirical formulas. So it is a bit extra work. Again, individual steps I think are not too difficult, but remembering how to piece them together and doing and not missing anything can be a challenge. So make sure you practice these problems with the opportunities you have. All right, any question on that type of analysis? All right, so that's sort of the major first half of today's class. We're going to move on to now is talking about amounts of substances that are involved in chemical reactions. So the real value of moles, I would say, is not so much in what we just talked about with determining composition, although it is useful. And usually moles on its own is not a quantity that's that relevant. But the reason that we use moles most often in a real chemistry context is to calculate the amounts of substances that are involved in chemical reactions. So again, thinking back to things we did way back in chapter 1, we talked about the law of conservation of mass, which says that the mass of substance that we put into a chemical reaction will be equal to the mass of the products that comes out. Mass is not created or destroyed. But if we want to calculate individually the specific amount of each reactant or product that's involved in a chemical reaction, that's going to involve mole conversions. But to be able to do that, we first need to generate what's called a balanced chemical equation. So we've kind of seen chemical equations already in some context, but not in a lot of detail. But basically, this is an equation that describes the chemical reaction, which is, again, a situation where the atoms and elements and or compounds are reorganized to form new substances. So you're not creating or destroying atoms, but you're reorganizing them, forming new bonds, forming new substances as a result. So in a chemical equation, you're going to arrange things in the following way. The reactants are going to be the elements and compounds that are consumed in a chemical reaction. Those can be thought of sort of as the ingredients that we put in. The products are going to be the elements and or compounds that are formed. So these are the things that come out of a chemical reaction. Reactants go in, products come out. And then in a balanced equation, each reactant and product, sort of given as its chemical formula, is going to have a coefficient in front of it. These are going to be numbers that are going to be in front of each symbol or formula. That tell you, and you can interpret these in two different ways, but they tell you either at a microscopic level the number of atoms or molecules of each substance that's reacting, or more useful, they also can relate to the number of moles of each substance that's reacting. So when we're doing this, you're going to have each substance in the chemical equation is going to have a number in front of it that tells you the relative number of either atoms or molecules, or more commonly moles of that substance. They can be interpreted in either way that are involved in the reaction. If there's no coefficient, it's assumed to be 1, but if there's anything else but 1 in front of that, that tells you that there's a different ratio of those substances involved. And again, the key aspect of balancing a chemical equation, of coming up with the correct chemical equation that has the correct coefficients on each side, is to remember what we learned back in chapter 1, which is that atoms, individual atoms, are neither created nor destroyed during a chemical reaction. So you're going to have each element is going to appear on both sides of the chemical equation, and on each side of the equation there needs to be the same number of that element on both sides. You can't have, again, one element converting to another. You can't have one just magically appearing or going away. So your coefficients allow you to do that. So let's go through the steps to balancing a chemical equation. The first thing to do is to arrange the reactants and the products. Sometimes we'll give you that to you and you just have to come up with the coefficients. Other times we will describe the chemical reaction to you and you have to then come up with the equation. So you're going to put reactants on the left, products on the right, separated by an arrow. And then you have to add the coefficients that are necessary to balance the number of atoms on each side of the arrow. Now, there's not always a right way to do this. For one type of chemical equation we're going to cover later on, we're going to learn kind of a prescribed method for doing it. But in most cases, it's just by inspection, kind of guessing and checking yourself. What is often helpful to do, and in some situations it's fairly obvious, in other cases there's often more than one way to start the problem. What I like to do is I like to set the most complex reactant or product to have a coefficient of 1. That being the one that has the most different atoms in the formula. That is sometimes a helpful starting point, and then you try to balance everything else relative to that. Because the hard part is you can't change the chemical formulas. Remember, all we're changing are the coefficients in front of the formulas. If you change the subscripts in the formulas, you're going to be changing the identity of the reaction or product. So you don't want to do that. You're just changing coefficients. But sometimes if you adjust one coefficient, you have to also adjust another one. You have to kind of go back and forth. If you set the most complex thing to 1, that sometimes limits the amount of guessing and checking you have to do to get it right. But there's different ways you'll have to do this depending on the situation you encounter. So this is just a recommendation that sometimes works. You're going to adjust the coefficients, as I said, to make sure that the atoms balance on each side of the arrow. They have the same number of each type of atom on both sides of the arrow. Typically, if we're asking you to balance a chemical equation, we will specify that we want whole number coefficients. It's not wrong to use fractional coefficients, and in some situations you will encounter those. But again, read the problem closely, and in most cases, if balancing the chemical equation is what we ask you to do, we will specify that your answer should have all whole number coefficients. And then it's good to check yourself if you have time, which again, the way you check yourself is to make sure that the number of atoms of each type on the left equals the number of atoms of each type on the right. So after you've added all the coefficients and you think you're done, it's good to double check that that's true if you have time. Now, something else you will sometimes see in chemical equations, it's not a huge deal right now, but if you see this, I don't want you to be confused by it, is that in a lot of times in a chemical equation, each reactant or product will have its state of matter indicated. For now, that's mostly going to be either S for solid. So you'll have a letter in parentheses after the reactant or product that tells you what it is in terms of its state of matter. S is solid, L for liquid, G for gas. We're going to talk in chapter 6 about another one, AQ for aqueous, which means that it's dissolved in water. So there's these little symbols that sometimes come into play at all. That doesn't affect how you balance the equation. That's just they're going to be there. And you just want to make sure that you're aware of what they mean, but we don't really need to worry about them too much for now. All right, so let's try this out for a few different equations. So one type of equation that is often involved in these sort of balancing exercises is a combustion reaction. So we talked about combustion analysis, which is burning something. And as we said, in a typical combustion reaction, CO2 and water are the two products. So here we're taking ethane, C2H6. We burn it in the presence of oxygen, and we form CO2 and water. So let's put the coefficients in that we need. So I wrote it out here multiple times just so we can kind of go through a stepwise process of getting it. But you don't need to necessarily write it out this many times. So like I said, a good starting point for these is to figure out which reactant or product is the most complex, which one has the most atoms in it. Now, all of these are either elements or binary compounds, so none of them are that complicated, but C2H6 has a total of 8 atoms in the formula, more than the rest. So as a good starting point, I'm going to set this to 1 and try to balance everything else relative to that. Now, the way that you typically will start out with balancing is look for an element that only appears once on each side of the arrow. All right, so we have carbon, hydrogen, and oxygen in this equation. But carbon only appears on the left side here and only appears on the right side as CO2. So carbon is an element that only appears once on each side. So if we set this coefficient to 1, there's 2 carbons in that formula. So we need a coefficient of 2 there to make sure that there's also 2 carbons on the product side. And then if we go to the other one that's on once on each side is hydrogen. Hydrogen appears here in C2H6 as a reactant and only appears in water on the product side. So there's 6 hydrogens in C2H6, and there's going to be then we need 6 on the product side as well. H2O has 2, so the coefficient needs to be 3. 3 times 2 is a total of 6. We didn't start with oxygen because oxygen appears only once on the reactant side, but appears in both products. So it's going to be unclear at the start what combination of coefficients we would need to balance oxygen. But now that we've set the coefficients for everything else, we can do the coefficient for O2 last. So on the product side right now, we have 2 times 2 oxygens for carbon dioxide. We have 3 oxygens from water, 1 each. So we have a total of 7 oxygen atoms on the right side of the equation, which means we have 7 on the left. Now, if O2 has 2 oxygens in it, for a total of 7, we would need a coefficient of either 3.5 or 7 over 2. So that makes sure we have 7 oxygens on both sides. Now, if we didn't specify that you had to use whole number coefficients, we could stop here. You'd have a fractional coefficient on O2. But if you want to get whole number coefficients, we have to get rid of that fraction. And again, the way that we do that is not by rounding, but by multiplying everything by some whole number that's going to get rid of the fraction. So if you have something over 2 or something 0.5, we can double everything. And again, though, we have to double every single coefficient. It's already balanced, so whatever we do to one coefficient, we have to do the same thing to the other in terms of multiplying or dividing. So if we double everything, we're going to get this 1 becomes a 2, the 7 halves becomes a 7, 2 times 2 is 4, 3 times 2 is 6. So that would be the smallest whole number set of coefficients that balances this equation. It's good to check ourselves now. So we look at each side of the equation and figure out if the number of elements on each side is the same. So for carbon on the left, we have 2 C2H6s, which is a total of 4 carbons. On the right, we have 4 CO2s. Each one has 1, so there's a total of 4. So that matches up. We'll do the same thing for oxygen and hydrogen. For hydrogen on the left side, we have 2 C2H6, so 2 times 6 is 12 for hydrogen. We have 6 H2Os. 6 times 2 is also 12, so hydrogen balances. And then oxygen, which is the trickier one because it appears in more places, but we had on the left side, we had 7 O2s, each with 2 oxygen atoms, so a total of 14 oxygens on the left. On the right, we have 4 CO2s that have 2 each. And we have 6 waters that have 1 each. So 4 times 2 plus 6 times 1 is also 14. So that's that last checking step you can do at the end to make sure you didn't miss anything. Add up the total number of atoms of each type on the left and make sure it matches what's on the right side for that element. All right, any questions on that? Now, this next one here, probably not as difficult to balance, but it's one where we have to formulate what the equation looks like in addition to just providing the coefficient. So Fe2O3 is the chemical formula for rust, iron 3 oxide, and it's formed by the reaction of iron element and oxygen gas, which has a formula of O2, write the balanced equation. We'll learn more about which elements are diatomic in the future, but in general, if you're not told otherwise, assume that any element just has that atom in the formula. So iron is just Fe by itself. That would be true for all metals. And then the other is going to reaction of iron with oxygen gas. So the other reaction is O2. And the product is rust, Fe2O3. So this is a situation where we had to read the information in the problem, translate that into what the equation looks like in terms of reactants on one side and products on the other. And so then we have to go through and start balancing it. As I said, the one that's most complicated will often start by setting that to 1. You don't have to write the 1 there, but I like to write it in just to remind myself that I'm fixing that coefficient at 1 and ideally not changing it after this. So on the right side now, we have 2 irons. Fe2O3 has 2 Fe's in the formula, so that gives us a coefficient of 2 here. And then similar story as last time. Our product has 3 oxygens. O2 has 2 in the formula, so we would need 3 halves or 1.5 as a coefficient there to give us 3 oxygens on each side. This one also ended up with a fractional coefficient, so if we want whole numbers, we need to double everything. And so this becomes 4Fe plus 3O2. We double all the coefficients, and then we get a 2 in front of Fe2O3 after that last step. All right, so that's the equation balanced with smallest whole numbers. We can check again that everything matches up on both sides. There's only 2 elements here, so it's a little bit simpler situation. So on the reactant side for iron, we have 4Fe. 4 times 1 is 4 total iron atoms. On the product side, we have 2 Fe2O3. Each one has 2 in the formula, so also 4 there. And then for oxygen on the left, we have 3 O2s that have a total of 6. And on the product side, we have 2 Fe2O3s. There's 3 oxygens in that formula, also 6. So again, good to check yourself at the end to make sure. All right, any last questions on balancing before I do one more slightly more complicated one? All right, this one is fun because not that you're going to see a problem like this, but because it was the first chemical reaction I did in a research lab as an undergraduate. So there's always that special connection to your first time doing anything, and this is not an exception to that. So the compound is cesium-4, rhenium-6, Se8I6, complicated formula, and you can make it by basically mixing up these 4 solids and just blasting it at 800 degrees Celsius for a few days. So write the balance equation and determine the sum of the coefficients. So the reason we're having you determine the sum of the coefficients here is it might not be as common anymore in WebAssign because WebAssign allows more complicated problem types than we had before. But sometimes in homework and test questions, because it's not always straightforward to have you write out the entire equation, we'll just ask for something like this, the sum of the coefficients, to test that you actually got it right, even though that's not a real important thing to know. So that's why I'm just giving that example here in case you see that. But we want to determine the sum of the coefficients on the reactant side when it's balanced with smallest whole numbers. All right, so a lot going on here, but we have rhenium metal, rhenium element, Se, cesium iodide, and I2, all reacting to make this beast of a compound, CS4, Re6, Se8, and I6. All right, now I think it's pretty clear what the most complicated chemical formula is in this equation. There's only one product and it has everything in it, so we'll set that to 1. And now we're going to balance everything on the left relative to that. Again, look for the elements that only appear once. The one that we're going to have to save until the end is iodine, because we have iodine here in the product that comes from both cesium iodide and from I2. So again, we're not going to really know which combination of coefficients on those is necessary to get 6 total iodines. We'll do that one last after we do the other one. So cesium appears in our product as CS4. So there's 4 cesiums in the product. So that means we need a coefficient of 4 there to have the same number of cesium atoms on both sides. Re6, rhenium is Re. 6 in the product, so we need a coefficient of 6 there on the left to balance that. 8 selenium's Se, so a coefficient of 8 there. Now we're ready to see if we need any coefficient on I2. So we don't want to change any coefficients ideally after we've already set them. But if we look at what's left, we have 6 iodines over here, 4 from this reactant, 2 more from I2. So I2 only needs a coefficient of 1 to balance that. So we don't need to add an additional coefficient there. So we have a total of 6 iodines on the left and right now, 4 from here, 2 from there, total of 6. Now this asks you for the sum on the reactant side, which again is not a useful parameter, but just something that we sometimes ask you to test you in problems like this that you did it correctly, just for making it easier to report the answer. So we have 6 from rhenium, 8 from selenium, 4 from cesium iodide. Now remember, we don't usually write in the ones, but they're there. So if that wasn't there, you have to remember that there's a coefficient of 1 implied. So don't forget that one. And so the total would be 19. Okay, so that's the one that you sometimes forget if it's not explicitly written out. All right, so that's just a last example of balancing. Slightly more complicated in terms of how it looks, but in the end, following the same approach works just fine. So any questions on that? All right, the next thing we're going to move into with the last little bit of time that we have left is stoichiometry. Stoichiometry is a scary word for some people, but it's one of the more important things we'll do. And again, if you're sort of following up until now what we've learned in terms of mole ratio, mole conversions and things, there's just really one extra step you have to add to do stoichiometry. So what is stoichiometry referring to? This is the process of calculating the amounts of reactants or products that are involved in a chemical reaction. I like that song, but cut it off too fast. Dancing Queen, is that right? Or what is it? I recognize that intro anywhere. All right. I don't want to embarrass the person that did that. It's okay. All right. So calculating the amounts of reactants and or products involved in a chemical reaction. The key concept here, we've already learned how to do a bunch of mole conversions. Those are going to still be involved in stoichiometry. So right now it's mass to moles primarily, but we also learned the definition of Avogadro's number, and we're going to cover a couple of others in later chapters. But the key concept is in stoichiometry is mole ratios, which is where we're going to use those coefficients from a balanced equation to tell us the relative numbers of moles of each substance that are in the reaction. So the coefficients in a balanced chemical equation tell us the relative numbers of moles of each substance that are involved in that reaction. So if we have a balanced chemical equation, I'm going to write out one that's totally fake and generic, but let's say we have 3A plus 2B. These are not real chemical symbols, obviously, in most cases. 4D, we have coefficients in front of each reactant and product. And then what we're going to be able to do in combination with other mole conversions is we're going to convert moles of one substance into moles of another by using those coefficients as ratios. So we can write ratios that say for every 3 moles of A that reacts, 2 moles of B react with it, or for every 3 moles of A reacts, we form 4 moles of D, or for every 2 moles of B that react, we form 4 moles of D, etc. So any combination of these two coefficients can be written as a ratio in either order that tells us if we want to convert moles of one substance that's involved into the moles of another substance that's involved in the same reaction, we're going to use the coefficients to do that because those coefficients can be written as or interpreted in terms of moles of each, and these are going to be then written as ratios. They're going to be unit factors. So it's really just dimensional analysis, converting moles of one thing into moles of another is kind of the key step in stoichiometry. Likely in combination with other mole conversions that we've been covering so far, but this is the key step for stoichiometry. All right. So then what that leads us to is sort of a flow chart, if you will, that allows us to diagram stoichiometry in kind of a pictorial way. So this is going to start with a sort of typical mass to mass stoichiometry problem, which is the most common type for this chapter, where the idea is you're going to be given the mass of one substance that's involved in a chemical equation. For example, this many grams of A reacts with this many grams of something else, or this many grams of A forms as a product. We can be given the mass of either reactants or products as a starting point, and the job is going to be to figure out what is the mass of another substance B that would be involved in that same chemical reaction. And again, A and B can both be reactants. They can both be products. One can be a reactant, one can be a product. Any combination of two substances that are somehow involved in that equation. Now, there's no direct single step that gets you from here to here. Remember, chemical equations are written as mole ratios, not as mass ratios. So typically, you can't just go straight from here to here. But what you can do is through a series of conversions, get there indirectly. So as I've been harping on this whole chapter, when in doubt, convert to moles. So if we can convert the mass of that substance that we're given into moles, by using its molar mass or molecular weight, that gets us moles of substance A. Then we can convert into moles of substance B or vice versa by using those reaction coefficients. of coefficients from the balanced chemical equation. So we have coefficients for A and B, and the ratio of those two allows us to convert one into the other in terms of the number of moles of each that are there. And then finally, if we want to get back to the mass of substance B as our ending point, we would use its molar mass to get back to there. So this process can start or end at any place. It can go in either direction, but these are the series of steps that are involved. So sometimes we might give you moles directly or have you find moles directly, so you don't have to go through this last step here, but other times, more typically mass to mass is the way to go. Just as a little bit of an aside, again, you can sometimes also have problems where you're going to use Avogadro's number to convert from moles into the number of atoms or molecules. Not very practical in most settings, but something we could ask you to do now that we know the definition of moles. So these are other mole conversions that could be involved as well. And similarly with substance B. Sorry. All right, so that's another sort of branching point that could sometimes come up. If we give you or ask you about the individual number of atoms and molecules, not just moles or mass, you would have to go through and do that. So we're going to learn a lot of different variations in stoichiometry. So I don't remember how many more I have, but we'll start here with this one. This is a reaction between gold nitric acid and hydrochloric acid to make this HAUCl4 and then release NO gas and produce water. How many molecules of water are formed when 2.56 grams of gold is reacted? So we're going to really treat these types of problems like really just big conversion factors, big conversions, where we're going to write out what we're looking for. We're looking for how many molecules of water are formed. And then we start with what we're given. We're told that 2.56 grams of Au gold is reacting. So our first step is going to be to convert whatever we're given into moles. Can't think of a stoichiometry problem where that wouldn't be the case, unless you're already given moles directly, which we're not here. So we use the atomic mass of gold from the periodic table. It's an element, so we can look that up to convert to moles. Now from here, which coefficients or which ratios we use depend on what we're looking for. So we're given the amount of gold, we're looking for an amount of water that forms. So those are going to be the two coefficients we use. We want gold to cancel, so that's going to go in the bottom. We're going to convert that into moles of water by using its coefficient. So from the balanced chemical equation, water has a coefficient of 2. Gold has a coefficient of 1. So for every 1 mole of gold that reacts, we form 2 moles of water. And we can write that as a ratio, 2/1. And then from there, we have to look at what we're asked for. So we don't usually stop at moles, but we often have to do another conversion to finish it. We're looking for the number of water molecules. So for that, if we want to know the number of atoms or molecules, we use Avogadro's number. There's 6.02 times 10 to the 23rd water molecules. And this last step is not very practical, but it's one that you could have to do in 1 mole of water. So that cancels out moles of water, it gets us to the number of water molecules, which is what we're looking for, so we stop. We get 1.56 times 10 to the 22nd. All right, so this is a what, 1, 2, at least 3-step problem here. 2 of those 3 steps we already covered earlier last time and today. And then really just this key stoichiometry step was involved with that. We probably have time for one more example. If I don't finish, whatever I don't finish, I'll write out in the notes, but I probably won't go over in detail since I'm gonna be gone for a while. But anyway, here's another one. Iron metal reacting with magnetite and hydrogen gas. Reacts with water, sorry, to form magnetite and hydrogen gas. How many grams of water are required to react completely to 25 grams of iron? So we need the balanced equation first. So iron metal Fe reacts with water, H2O. Hopefully you know the formula of water by now. This is another iron oxide that's a little bit different than rust. It's called magnetite, Fe3O4, has magnetic properties as the name suggests, and then H2 gas. All right, so we're going to balance the equation. I'm going to go through this quickly because I don't have a ton of time left, but we need a 4 there to balance. Sorry, I'm skipping steps here. We're going to set this as 1. That means we need 3 Fe, 4 oxygens, and then we have 4 oxygens. There's a total of 8 hydrogens, so we need 4 H2s as a product. So I'll skip all the checking, but there's basically 3 irons and 3 irons. 4 times 2 is 8 for hydrogen, 8 over there. 4 oxygens, 4 oxygens. So that's the balanced equation. If you're doing a stoichiometry problem, you have to have that before you can do anything else. So if it's not given to you, you do have to produce it. Oftentimes it will be given. Next, we're ready to set up the problem. So we have 3 Fe, 4 H2Os, forming Fe3O4 and hydrogen gas. Okay. So we want to know how many grams of water are required to react with 25.0 grams of iron. So we're looking for grams of water, and we're given the amount of iron that's involved, 25.0 grams. Our first step is going to be convert that into moles. So 1 mole of Fe has a mass of 55.85 grams. That's the number from the periodic table, the atomic mass of iron. We've gotten moles of one substance, but we're going to convert now to moles of the other substance that we're interested in, which is water, by using the ratios from the balanced equation. So we want to figure out how many moles of water there are, we want moles of Fe to cancel, and we use their respective coefficients. Water has a coefficient of 4. Iron has a coefficient of 3. I implore you to always write out units and quantities very specifically so you know that the 4 goes on the top and the 3 goes on the bottom. Because again, we want moles of iron to cancel, so that has to go on the bottom. We want moles of oxygen, or moles of water, sorry, to be in the numerator, so that goes up there. If you're not writing things out carefully, it's easy to flip that or not know what you're supposed to do. And then the last step is we're trying to find grams of water. So once we have moles, we can get back to grams using the molar mass. So 1 mole of water has a mass of 18.02 grams. That's the molar mass of H2O, 2 hydrogens plus 1 oxygen. We've gotten to grams of water, so we stop there. So this is more of a, I guess, 4-step, still 3 steps, I suppose, but typical mass to mass. Start with mass of one thing, end up with mass of another. That gives us 10.8 grams of H2O. All right. You guys can't put stuff away yet because this is our first bonus quiz. That's one of the reasons I was rushing to finish that one. So since you guys are all here today, you're going to be getting access to this. Anybody that's not here, well, come next time so you can do the bonus quiz, or next time we have it. All right, this is going to get a little bit chaotic, so I'm going to stop the recording because people on YouTube don't need to see this chaos. It's just a quick problem that should take you like a minute to do. It's going to take me longer to pass out the forms than it will to do that. So